Yeah.
I am here.
Yes, sir. So
Yes.
I
we
just had to turn
start
on.
the session. Yeah.
We can start, sir.
Oh, okay. I would like to introduce Professor Ayman Badawi, and I see that he has had a lot of education in the United States, including a PhD from the University of North Texas, which is a place I had a good friend at. But his most interesting part of his CV is he claims three languages, which is Arabic, English, and mathematics. And I am very happy to say that I can almost compete with you because I know two languages, English and mathematics. So I congratulate everybody here who speaks English who is not a native English speaker. I always am grateful to you for your ability to communicate with me without my having to work at it. Anyway, Professor Badawi has many research papers, about 50 research papers, and has edited two books and three books, excuse me, and been a co author or author of two books. And I must say that writing a book is a major task, and I admire that as well. And I see that you have also given a great many speeches or lectures on four different continents plus Hawaii, which is also a very nice attribute, including Africa, by the way, which I have never given a talk at, but one day I hope I will. Now, I see also that Professor Badawi has some editorships of several journals, and one of them is a journal to which I will submit an article some year, and that is the Journal of Quasi Groups and Related Systems. So I see that your interests lie in basically algebra and ring theory, but with some detours, such as into quasi groups and related systems, where you have modified algebraic structures, and you have gotten into graph theory. So, welcome into graph theory, and welcome to this conference. I
Okay.
turn it over to you now.
Well, first, thank you very much for the introduction, and I hope one day I will meet with you face to face. Uh, Thank you very much.
So,
Okay.
with your kind permission, excuse me, sir, with your kind permission, may we record the session?
Yeah. Well, this is a talk. Uh, it's just like for general talk. Uh, is not published anywhere, and I don't think it will be published. It is just a new look at the zero divisor graph using number theory. And I have to be careful here. So, by saying that, maybe some of you think that uh, I can use basic number theory to do many of the fancy things about about zero divisor graph. No, this is not the case. Here I'm assuming that uh, if there are students that there is no background in ring theory, uh, and the method I'm gonna use just using very basic number theory uh, to come up with similar result uh, uh, on zero divisor graph. In fact, I gave this talk uh, maybe 2 years ago in Mysore University in honor of Professor Adigar, I believe that's the name, because he is a number theorist. And so I was thinking how I gonna, like combine graph theory with number theory. So I came up with this idea. I tried to come up, uh, with similar results using only basic number theory. Okay, and again, let me remind you with this famous paper in 1999. Uh, if you let R to be a commutative ring with 1 not equal 0, and ZR star is the set of all non-zero zero divisors of R, then the zero divisor graph of R, denoted by this, is undirected symbol graph with vertex set the non-zero zero divisor, and two distinct vertices are connected by an edge if and only if AB equals 0. Okay? So this is the definition when you study commutative rings in general. And definitely to study this graph, you need to know ring theory. But in this talk, I'm gonna focus only on the integers modulo m. When you focus on the integers modulo m, then, maybe you can do, things using only number theory. So if you want to follow my talk, uh, you need to know what I mean with Vm and Um. So you choose a positive non-prime integer m, and you take all the numbers between 0 and m, where the GCD between a and m not equal 1, and all the numbers between 0 and m, where the GCD between a and m is 1. And this graph M, is symbol directed, and two vertices are connected by an edge if and only if AB equal MK for some integer K in Z. So let me stop here, because when you are inside Zm, the integers modulo M, let's what does it mean that AB equals 0? AB equals 0, that means AB is multiple of M. So you see how I translated the general definition for any ring to integers modulo M. Okay? Because in the general definition, when you have a ring and you select two vertices, then AB will be connected by an edge if and only if AB equals 0. Okay? So when you want to translate that to the integers modulo M, this will mean AB equal MK for some integer K in Z. And definitely VM, V indexed by M, this is the set of non-zero zero divisor of the ring ZM, right? So my VM here is ZR star, the set of non-zero zero divisor. And my UM definitely is the set of unit. So two vertices in VM are connected by an edge if and only if the product is multiple of M. That's exactly what this means. Okay? All right, so as an example here, like if you take m equals 60, then we know the cardinality of UM is phi 60, which is 16 element, where the cardinality of VM will be this number, right? Because every element in ZM uh, is either what? Is either zero divisor or a unit, okay? And why did I do 59 minus 16? Because I'm removing the zero. Because my VM consists of non-zero zero divisors. Okay, so okay, I'm gonna consider cases. What about if M is Q square for some positive prime Q? And I want to study this graph, the zero divisor graph, uh, using this number, using this M. Then definitely, the cardinality of VM will be bigger or equal to 2. And if you have A, B, and VM, then definitely A will look like a unit times Q, and B will be V times Q, where U and V are some units in ZM. What I mean with unit, by the way, since I'm using inside ZM, uh, a number inside ZM will be a unit if the GCD with M is 1. So I can write A as UQ, B equal VQ, where U comma V, both of them, the GCD between U and M is 1, and V and M is 1. And remember, M is Q square. Then definitely you have this edge. And here I assume Q is not 2. So that means this graph will be complete, right? When you have this. What about the general case? If you take M to be Q to the N, where Q is some prime integer. Here we split that into when Q is 2 and N is 3, then definitely the set of vertices will be 2, 4, 6. Okay? And I can split the set of vertices into two set. One of them is A and the other one is B. And you can check that this graph will be complete bipartite, K1, 2. Okay? All right. Uh, so as you see here, from so far, I'm not using the language of ring theory or ideal, or I'm just using very basic number theory. And I want to repeat, so I will not mislead you again. This is not a substitute for the original definition of zero divisor graph. This is okay as long as I'm talking about the integers modulo m. Okay. Anyway, and you can do the same thing when q equal 2 and n 4. Then you look at this 2 to the n is a vertex, and 2 to the n. Remember, what are the vertices in ZM? All the numbers between 0 and m where the GCD with M not equal 1. That means they are zero divisors, non-zero zero divisor. So here I form a cycle of length 3. It's clear, like this vertex with this vertex, if you multiply them, then they are multiple of 16, I believe. Yeah, n bigger or equal to 4. Yeah. So when you multiply them, you get 2 to the n. And remember, my m is q to the n. Anyway, and the girth is 3. By the way, what do we mean with girth? I think all of us know the girth of the graph is the length of the shortest cycle in the graph, right? Um, okay. And the same thing, I'm doing the same thing for, uh, uh, you know, q to the n in general. So what about the case when m is a product of 2 prime? So remember the first case I considered where my m is sum prime to the power n. So the second question you're going to ask me, what about if m is a product of 2 prime, distinct prime? Well, then we know how are the vertices in Zm. The okay, again, let me remind you with Vm. Vm, if you have A and B in Vm, that means the GCD between A and M is not 1. The GCD between B and M is not 1, right? So you need to consider 3 cases. What about if A is equal UQ1, B equal VQ2, where V and U are some unit? Unit meaning the GCD with M is 1. So definitely here is an edge. What about if you have A is this using the same prime? A equal UQ1, B equal VQ1. Then definitely I can insert Q2 between A and B, and then I can walk from A to Q2 and then to B, right? And the same thing if A is multiple of Q2, A and B both, then I can insert the Q1 between them. So that means I always get a connected graph. And when M is a product of 2 prime, it's clearly the diameter of the graph will be 2, right? The diameter will be 2. And to see that, as you see, I'm not using any fancy thing except basic number theory from maybe high school or college or things like that. Okay. Then you go to the case when you have a q1 to the m and a q2 to the n. Like your m, still q1 and q2 are distinct prime, but m, maybe I should not use m here, but it's too late. I have m equal q1 to the m, but you know what I mean, like a q1 to the l maybe, or I, or k. This m is different from this m. Anyway, and you can play with the same game here, you know, studying the zero divisor graph, and I show you a way how you split the vertices into two set, A and B, okay? Here I consider M and N is 1. For this case here, if you read below, case 2, where N and instead of M, let's call it K, K and N, for some K bigger than 1 and N bigger than 1, okay? And down here, I continue with the first case, or not the first, the case where M is a product of 2 prime. Then, okay, uh, so I have M is a Q1, a Q2, and I took A to be this set and B to be this set. Then definitely the union will give you VM. Remember, VM are all the numbers between 0 and M where the GCD is not 1. So I can form complete bipartite. That's what this about. Okay, and here I will have similar result. I hope I made, like when M equal to square Q. Here is one thing. Let me also to be, like using basic number theory. Yes, I can study the zero divisory graph of ZM. But as you see, I'm considering many cases using, the basic, where if you know ring theory, all these, what I'm talking about, can be done in one or two results. Okay? So the question you're gonna ask me, why am I doing that? Well, as I told you, I'm doing it because I'm giving a talk, a general talk, and I don't want to use the terms of, prime ideal and maximal ideal and a quotient ring and so on. So I'm trying to give you a feeling to the zero divisory graph of the integers modulo m using basic number theory. Okay? Uh, and you can do the same thing. Let me see here. Yeah, it's all playing the same. I mean, now you get the idea. And yeah, I end up, I think, I gave you what you can do with that. Uh, Here is m be positive non-prime integer, and you write m as a product of these. And then we look at the domination number of this graph. We claim this graph, the domination number is n. And remember what's the domination number, or maybe like it's a set of vertices where let's call it D, where every vertex of the graph outside D is connected to at least one vertex in D. And I think domination number is kind of, it's very important concept in graph theory. And in fact, it's a hard problem. It is not always easy to find the domination number. Okay? So the domination number for the graph I'm studying here is going to be always n. And what is n? If you look at n is the number of the distinct prime factors of m. So if you factor m in the factorization of m, if you are using 10 distinct prime, then the domination number will be 10. And here I constructed the set, the dominating set for any m. Again, in zero divisory graph, I think there are some result on the domination number for any ring or for most of rings. Uh, anyway, but here again, I'm calculating the dominating number or domination number using basic number theory. I hope I mean I entertain you with this with this talk. It's very basic, uh, but maybe there are some student and maybe they will. Anyway, thank you very much, and I thank you for the invitation. And I'm so sorry I cannot attend, all talks and all session because I have other duties at the university. And there is good news. I just received an email now from the university. They announce that next semester is going to be fully face-to-face. So that's a good news because now we are doing hybrid. Like some classes are face-to-face and some are online. It depends on the size of the classroom. Yeah, so this is, I hope to meet. I mean, India is like I am a regular customer to India. Usually, I visit India maybe 4 or 5 times in a year. And maybe very soon I'm gonna apply for Indian citizenship. Uh, Okay, thank you very much, and thank you, Professor, for introducing me, and I wish you all best.
Thank you, Professor. Thank you for accepting our invitation.